So question number 8, a cell supplies a current of 0.9 amps through a 2 ohm resistor and a current of 0.3 amps through a 7 ohm resistor. Calculate the internal resistance of this cell. Okay, so what we are going to do is we are going to use the equation that relates internal resistance, external resistance, EMF and voltage. Okay, so here we have a cell with some internal resistance. So when the external resistance added is 2 ohms, the current is 0.9 amps. And for the same cell, when the external resistance capital R is 7 ohms, the current is 0.3 amps. So with these two data, we are going to calculate the internal resistance of the cell. Okay, so we know the internal resistance R is equal to epsilon minus V by V into R. Okay, so for this first case, V1 is equal to I1 R1. So I1 is 0.9 into 2, V1 is equal to 1.8 volt. Similarly, V2 is equal to I2 R2. So I2 is 0.3 into R2 is 7. So V2 is 2.1 volt. So using the first data, R is equal to epsilon minus V1 by V1 into R1, and R is also equal to epsilon minus V2 by V2 into R2. So R is equal to epsilon minus 1.8 by 1.8 into 2. R is also equal to epsilon minus 2.1 by 2.1 into 7. So cancelling this comes around 0.9, this one 0.3. So take this side, 0.9 R is equal to epsilon minus 1.8. Here 0.3 R is equal to epsilon minus 2.1. From this, epsilon is equal to 0.9 R plus 1.8. Here epsilon is equal to 0.3 R plus 2.1. Both are E, so I can relate 0.9 R plus 1.8 is equal to 0.3 R plus 2.1. Take this side. 0.9 R minus 0.3 R is equal to 2.1 minus 1.8. So 0.6 R is equal to 0.3. R is equal to 0.3 by 0.6 is equal to 1 by 2. So the internal resistance R is equal to 0.5 ohms. That's it. The answer is given as 0.5 ohms. Okay, that's it. Question number 9, calculate the currents in the following circuit. So there is a circuit given. You are asked to find I1, I2 and I3. So for this problem, you are going to use Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law is junction rule and Kirchhoff's voltage law is a loop or mesh rule. Okay. So what is Kirchhoff's current law? Kirchhoff's current law states that the algebraic sum of current at any junction is 0. What does that mean? Current entering is equal to, total current entering is equal to total current leaving. And Kirchhoff's voltage law states that for a mesh or a loop, the net EMF is equal to the sum of the product of current into resistance, where I is equal to 1 to N. Okay. So before starting, we have to name the nodes A, B, C, D, E and F. Okay. So first apply Kirchhoff's current law at junction B. B is a junction, okay? So what are all the currents associated at B? I1 is entering, I2 is leaving, and I3 is leaving. So what is entering is I1, what are leaving currents are I2 plus I3. So from this we can write I3 is equal to I1 plus I2. Does it make sense? No. I1 minus I2. Okay? Right. Now apply Kirchhoff's voltage law for loop, first loop A, B, E, F, A. A, B, E, F, A. Okay? So when you try to solve a loop for using Kirchhoff's voltage law, you have to indicate the tracing direction. So you start from here, then go in this direction, come in this direction, go in this direction. So is it necessary to go this way? No, you can go in the opposite direction also. Okay, so I have chosen to move in this direction. This is the direction of current flowing. Okay, so this being the EMF source, this is the positive terminal, and usually current is drawn from this end, conventional current. This is I1. So I1 goes here, and at B it gets split, divided into I2 and I3, and I2 gets into this circuit and I3 through here. And at this point what is coming is I3, and what is coming here is I2. I2 plus I3 again becomes I1, and a steady current flows through this circuit. Okay, so applying Kirchhoff's voltage law for loop A, B, E, F, A, I move in this direction. So this is positive. The EMF, there is only one EMF source, so the net is the same. So 15 is equal to, right side, product of I and R, and if there are 5 resistances, you are going to add that resistances multiplied by the current. Okay, so this is 15 is equal to I1 flows here, and a part of the current I1 is flowing through the secondary circuit. I3 is coming here. So what is coming down is I3, and the tracing direction is also the same. So the resistance here is 100 ohms. So you can write it as 100 into I3, and the tracing direction is this way, and the current is also in the same direction, but this current is I1, it is also passing through 100 ohms. So plus 100 I1. So 15 is equal to 100, I3 is equal to I1 minus I2 plus 100 I1. Okay, so 15 is equal to 200 I1 minus 100 I2. This is equation 1 obtained for loop ABFA. This is 1. Next, apply Kirchhoff's voltage law to the loop B, C, D, E, B. Here also you draw the direction. I go this way, come down, go left, and go up. Okay. See, this is the current direction. This is also the current direction. But if you look at the EMF, it looks like the current is drawn from the negative terminal. But usually conventional current is drawn from the positive terminal. So in the left side, I have to take it as minus 9 is equal to, why minus 9? So the current is drawn from the negative end, so it is opposite to the conventional current. So you have to take it as minus 9. And you are coming down. What is coming down is I2. I2 is flowing through 100. Tracing direction is same as the current direction. So this is equal to 100 I2. And then you go this way and go up. So I3 is coming down, but the tracing direction is up. So you have to take it as minus 100 into I3. So minus 9 is equal to 100 I2 minus 100 I1 plus 100 I2. What have I done? I3 is equal to I1 minus I2. Substitute that. So minus 9 is equal to 200 I2 minus 100 I1. Okay, this is equation 2 obtained for the second loop BCDEB. Solve these two equations. Okay, so what we are going to do is write the first equation as such: 15 is equal to 200 I1 minus 100 I2. Multiply second equation by 2. So minus 9 is minus 18. Minus 100 I1 is minus 200 I1 plus 200 I2 is plus 400 I2. Okay, so solving, minus 3 is equal to 300 I2. So I2 is equal to minus 3 by 300, which is minus 0.01 amps. So I2 is equal to minus 0.01 amps. Okay. So you substitute I2 in any one of the equation, right? So 15 is equal to 200 I1 minus 100 into I2 is minus 0.01. So 15 is equal to 200 I1 plus 1. So 200 I1 is equal to 15 minus 1, which is 14. I1 is equal to 14 by 200, that is 7 by 100, which is 0.07 amps. So I1 is equal to 0.07 amps. Okay. What is I3 is equal to? I3 is equal to, I3 is equal to I1 minus I2. So I1 minus I2, which is 0.07 minus 0.01. So I3 is equal to 0.08 amps. Okay. That's it. So actually the assumed direction is opposite. See, I2 is in this direction, but I2 we have found it as minus 0.01. That means, listen, I'll use a different color to show you. I'll use this red. See, I1 is 0.07 amps flowing in this direction. I2 is not in this direction. Minus means I2 is flowing in this direction. I2 is equal to 0.01. So at B, I1 is 0.07, I2 is 0.01. Both combined and I3 becomes 0.08 amps. Does it make sense? Yes, good. Question number 10. A potentiometer wire has a length of 4 meters and a resistance of 20 ohm. It is connected in series with a resistance of 2980 ohm and a cell of EM of 4 volt. Calculate the potential gradient along the wire. Okay. So the resistance on the potentiometer wire is 20 ohm. It is connected in series with another resistance of value of 2980 ohm. So these two resistors are connected in series, right? So R series or R equivalence is equal to 20 ohms plus 2980 ohm, which comes around 3000 ohm. This is R series. So the current flowing I is equal to V by R. So V is 4 volt, right? So 4 by 3000, which is 1 by 750 or which is 0.0013 amps. So the current flowing through the circuit I is equal to 1.3 into 10 power minus 3 amps. Okay, this is the current flowing through the circuit. Okay, but we are asked to find the potential gradient along the length of the potentiometer wire. So V between the terminals is V is equal to I into R. Okay, so the current flowing through the circuit is 1.3 into 10 power minus 3 into the resistance on the potentiometer wire is only 20. So we are calculating this. V is the potential difference between the ends of the potentiometer wire. So V is equal to, V along the potentiometer wire is equal to 0.0266. Okay, this is potential difference between the ends of the potentiometer wire. Potential gradient is, what is gradient? So the potential is changing along the length. So the difference in potential by L, that is V by L. So 0.0266 divided by total length of the wire is 4. So this comes around potential gradient V by L is equal to 0.66 into 10 power minus 2. What is the unit? Voltage per meter. That's it. Got it? Right. So question number 11, determine the current flowing through the galvanometer G as shown in the figure. So this is a circuit. We are going to use Kirchhoff's current and voltage law. So I'll use Kirchhoff's voltage law for the two loops, loop 1 and 2. Loop 1 is P, Q, S and P. P, Q, S, P. And loop 2 is Q, R, S, Q. Q, R, S, Q. So if you want to use the Kirchhoff's voltage law, you have to indicate the trace direction. So this is indicated here. I go this way, come down and go this way. Okay. So there is no EMF source here. So left side is 0 for P, Q, S, P. Left side is 0, which is equal to, I go this way. Current direction is also same as the trace direction. So this is equal to 5I1 and the trace direction comes down and current direction Ig is also in the downward direction. So this is the galvanometer resistance is 10 ohms. So this is plus 10 into Ig, and then the trace diagram, the direction is this direction, but current direction is in the opposite direction. So I have to use minus. Resistance is 15, current is I2, minus 15 I2. Okay. And for loop QRSQ, again even in this mesh, this QRSQ, there is no EMF source. So left side is 0 and I go in this direction. This is the trace direction and current flow direction is also the same. So 10 into the current flowing through 10 ohms is I1 minus Ig, and then trace direction is this direction, but current direction is in this direction. So again minus 20 into I2 plus Ig. Okay. And then trace direction is upward, Ig is downward. So again minus minus 10 Ig. Okay. So at junction P, using Kirchhoff's current law, what is entering is 2 amps. 2 amps is split into I1 and I2. So 2 is equal to I1 plus I2, or wherever you face I2, use 2 minus I1. Okay. We have two measures, so you get two equations, but there are three unknowns. What are the unknowns? I1, I2 and Ig. Okay, so you have to make I2 in terms of I1, so that now the unknowns are only I1 and Ig. Am I making it clear? Right. Now let us substitute I2 is equal to 2 minus I1. Let this be equation 1. So I split it, 10 I1 minus 10 Ig minus 20 I2 minus 20 Ig minus 10 Ig. So this is 10 I1, 10, 20, 30, 40 minus 40 Ig minus 20 I2. This is equation 2. Okay. So write equation 1 first. 5 I1 plus 10 Ig minus 15 I2. I2 is 2 minus I1 is equal to 0. So 5 I1 plus 10 Ig minus 30 plus 15 I1 is equal to 0. This is 15, this is 5. 20 I1 plus 10 Ig is equal to 30. Okay, this is 1. So second equation is 10 I1 minus 40 Ig minus 20 into 2 minus I1 is equal to 0. So 10 I1 minus 40 Ig minus 40 plus 20 I1 is equal to 0. So 30 I1 minus 40 Ig is equal to 40. This is equation 2, and you are going to solve equation 1 and 2. Okay. Now multiply first equation by 4. This is the first equation, multiply it by 4. 80 I1 plus 40 Ig is equal to 120. Second equation, 30 I1 minus 40 Ig is equal to 40. Adding the two equations, 110 I1 is equal to 160. I1 is equal to 160 by 110, which is 16 by 11 amps. So I1 is equal to 16 by 11 amps. To find Ig, substitute it in any one of the equations. Okay. So I'll substitute in this equation. 30 I1 minus 40 Ig is equal to 40. 30 into 16 by 11 minus 40 Ig is equal to 40. Okay. We divide it by 40. 4 3s are 12. 12 by 11 minus 1 minus Ig is equal to 1. Ig is equal to 12 by 11 minus 1 is equal to 12 minus 11 by 11. So Ig is equal to 1 by 11 amps. 1 by 11 is 0.09, or Ig is equal to 0.09 amps. That's it. So question number 12, two cells each of 5 volt are connected in series with a 8 ohm resistor and 3 parallel resistors of 4 ohm, 6 ohm and 12 ohm. Draw a circuit diagram for the above arrangement. Calculate the current drawn from the cells and current through each resistor. Okay. So first draw the circuit diagram. There are two cells of each of 5 volt. Okay. This is connected in series with the 8 ohm resistor. Let this be our 8 ohm resistor. This is connected to 3 resistors connected in parallel. Let this be 4, this be 6 and this be 12. Okay. This is 5 volt and this is 5 volt. Minus plus, minus plus. So current is drawn and it passes through here. Let this be R1, R2, R3 and R4. So R2 is 4 ohms, this is 6 ohms and this is 12 ohms. See, R2, R3 and R4 are parallel. So 1 by R parallel is equal to 1 by R2 plus 1 by R3 plus 1 by R4, which is 1 by 4 plus 1 by 6 plus 1 by 12. So this comes around 4, 12, 3 plus 2, 4 plus 1 plus 2. So this is, take 12, this is 3 plus 2 plus 1, which is 6 by 12, 1 by 2. So 1 by Rp is equal to 1 by 2. That means Rp is equal to 2 ohms. Okay. Now this can be drawn like current is drawn. This is 5 volt and this is 5 volt. This is R1, which is 8 ohm. This is Rp, which is 2 ohm. Now this can be made as okay. This is 5 volt. This is 5 volt. I. This is R equivalence. See, this 8 ohms and this 2 ohms are in series. So R equivalence is equal to 8 plus 2, which is 10 ohms. So this is our R equivalence, 10 ohm. I is equal to V by R. What is the total voltage EMF supplied? 5 plus 5 is 10 by total is 10 ohm. So 1 amps. So the current drawn from these cells I is equal to 1 amps. Next you are asked to find the current through each resistor. Okay. So when the resistors are connected in series like here, the current is the same. 1 amp is going to be the same, but the voltage gets divided. Okay, so the 10 volt is divided among this 8 ohm and this combined parallel 4, 6 and 12 ohms, which is 2 ohms. Okay, so to find that, V across R1 is equal to I1 R1. I1 is 1 into R1 is 8. This is 8 volt. So V through R1 is 8 volt. So V after this, V across the parallel combination is 2 volt. Okay, how do you get this? V parallel combination is equal to I parallel and R parallel. I parallel is 1, R parallel is 2, so this is 2 volt. So voltage drop across 4 ohm, 6 ohm and 12 ohms are 2 volt. Therefore, I across 4 ohm is equal to V by R. What is V? 2 by R is 4. So 0.5 amps. I through 6 ohms is equal to 2 by 6, which is 1 by 3 or 0.33 amps. I12 is equal to 2 by 12 is 1 by 6, which is 0.17 amps. Therefore, current through 8 ohms is equal to 1 amps. Current through 4 ohms is equal to 0.5 amps. Current through 6 ohms is equal to 0.33 amps. Current through 12 ohms is equal to 0.17 amps. These are not ohms, these are amps. Okay. So you add all these three, what you get is again 1 amps. Okay, that's it. Question number 13. 4 bulbs PQRS are connected in a circuit of unknown arrangement. When each bulb is removed one at a time and replaced, the following behavior is observed. See, there are 4 bulbs P, Q, R and S, and the arrangement is not given, and you are asked to get the circuit diagram for these bulbs. But what they are up to is they remove one bulb at a time. So first P is removed, then Q is removed, R is removed and S is removed. See, first P is removed and check which bulbs are glowing. Then you have to put it back. You have to put P back and then you remove Q and check for which bulbs are glowing. After that, you put Q back and remove R. So you are removing one at a time, and then before removing the next one, you have to put the removed one back. Okay, it is not that you are removing P first and then Q second. That means the circuit is out of P and Q. Nothing like that. So you remove P and check for the functionality of the circuit, and then put P back and then remove Q, and then check for the functionality, and then put Q back and remove S. Okay, so the circuit is without only one bulb at a time. Okay, so we have 4 bulbs P, Q, R, S and connected. Okay, you just check for this. If you are removing P, there is no P on or off. No, P is not there. Q is removed, Q is not there. R is removed, R is not there. S is removed, S is not there. Okay. See, when P is removed, all the 3 bulbs are glowing. So it doesn't matter whether P is there or not. If P is there, all the remaining 3 are glowing. Even if you remove P, again all the 3 are glowing. Okay. First thing. Second thing, you remove Q. When Q is removed, only S, bulb S is off. P and R are in on condition. When R is removed, all the 3 bulbs are in off condition. So all the 3 bulbs are in off condition means R is like a switch. So R needs to be there for the rest of the bulbs or remaining bulbs to glow. Okay. And then when S is removed, only Q is off and P and R are on. So how to take it? First you have to see when R is removed. This is very important and a key factor. When R is removed, all the bulbs are off. So you can take an EMF source. Okay, this is my EMF source. Current is drawn from here. It has to pass through bulb R before going to the other remaining 3 bulbs. So it has to pass through, let this be plus terminal minus, it has to pass through R and it is coming to this point. And then see, when Q is removed, S is off. When S is removed, Q is off. See, when Q is removed, S off. When S is removed, Q off. That means Q and S are in series connection. You understand? So in series connection, if you remove one, the circuit will be open and there will be no flow of current. So you again check, when Q is removed, S is off. When S is removed, Q is off. That means Q and S are in series. Okay. So beyond this, what I'm going to do is, this is my Q and this is my S. Okay. P is not there. Even P is not there. All the 3 are in on condition. So the current is drawn from here. See, it is like resistors in series. So it flows through all the resistors. Okay, all the bulbs. But P has to come somewhere. P does not hold any role in turning the bulbs off, but it is also there. That means it is parallel to this is P. Okay. This is the circuit diagram. When R is not there, P, Q, S off. That means R is like a switch. When Q is not there, only S is off. That means Q and S are in series. S is removed, only Q is off. So this means Q and S are in series. If P is removed, it does not affect this circuit. All the 3, Q, R and S, are on. That means P is in parallel combination. Parallel combination to Q and S. Okay, that's it. So question number 14. In a potentiometer arrangement, a cell of EMF 1.25 volt gives a balance point at 35 centimeter length of wire. If the cell is replaced by another cell and the balance point shifts to 63 centimeter, what is the EMF of the second cell? Okay, so we have learned the applications of potentiometer, where the potentiometer can be used first thing to calculate the internal resistance of a cell, and second one is to compare the EMFs of 2 cells. So when the EMF of the cell is 1.25 volt, the balancing length L1 is 35 centimeter. Okay, and then when this cell is changed with a cell of different EMF which is not known, the balancing length L2 is like 63 centimeter. So we know that epsilon EMF is proportional to length. So epsilon 2 by epsilon 1 is equal to L2 by L1. From this, epsilon 2 is equal to epsilon 1 into L2 by L1, which is 1.25 into 63 by 35. So the EMF of the second cell comes around 2.25 volt. Okay, that's it.